All right, in this lesson here, we're going to take a look at how to turn word equations into balanced chemical equations. Okay, now there's a specific progression you need to take. And a lot of times, most mistakes come from getting kind of messed up on that progression and trying to do one thing before you should do, when you should do something else. So I want you to take a look at this colored list over here, 1, 2, and 3. This is the progression we need to take. And I put these in different colors so that hopefully you can recognize these parts show up within these equations so you know what to watch for. So when we're going to write a balanced chemical equation and all we have is the names of the reactants and products to work with, what we have to do is we have to first look for diatomic elements. Okay? And there are 7 diatomic elements. These are the elements we talked about in class. There's 7 of them, of these nonmetals, that happen to be found in pairs. So when you find them in nature, they're always doubled up. Okay, for example, you'll never see a chlorine atom just floating around by itself. It's always paired up and bonded with another one, and that's so the two of them can be happy and achieve stability. Okay, so all 7 of these, if they're by themselves, they always have a little 2 after them. Now, if they're not by themselves, and what I mean by that, if nitrogen is not just pure nitrogen, but it's bonded to something else like, say, potassium, then that 2 doesn't need to be there. It's all based on how many electrons one would lose and the other would gain. So it goes back to the charges we talked about, the oxidation numbers. So this only applies if they're alone. So first we're going to look for diatomics. Then the next thing we're going to do is we're going to take a look at chemical formulas. Okay, we're going to look at specific compounds and we're going to figure out if they're ionic, and if they are, we have to look up their charges. And if they're covalent, which means they're all nonmetals, then we don't have to worry about looking up charges, but we have to take the prefixes in the name and interpret what that means in terms of a chemical formula. That's the big key. That's one of the major spots that a lot of people will take a wrong turn on. Once that's done, we're going to balance the amounts, but that always comes at the very end. We always balance the amounts very last after we have the correct identity of everything involved. So let's take a look at a few examples. Okay, we're going to start with what I have up here in blue. Sodium plus calcium phosphate yields calcium plus sodium phosphate. Okay, so we have 4 different things there. Now I'm going to look to see if there's any diatomic elements. Okay, I want to know if any of these 7 elements show up by themselves. So I look up here at the only things that are single elements. Sodium is a single element, and calcium is a single element. Those are both metals. Neither one of them show up here, so I have no diatomics to worry about. Okay, what that means is I can just take sodium and I can write Na. Okay, it's not diatomic. There's nothing special about it. It's just a plain old metal. So I just have single sodium atoms right there. Okay, I'll put a little plus sign, and over here I can write Ca and a little plus sign. Both of those are not diatomic, so I just write their formula from the periodic table. All right, so I've looked for all the single elements. None of them happen to be diatomic, so I'm just going to write them as single elements. The next thing is I have to deal with charges on anything that's ionic. And remember, ionic means there is a metal involved. There's a positive ion at the beginning. So when I look up here, calcium is combined with this combination of nonmetals, one of our polyatomic ions. So I'm going to look up the charges on both. Okay, calcium on the periodic table happens to be a +2. And when I flip it over on the back and I see those polyatomic groupings, phosphate is a -3. Those don't make 0, so I know I'm going to need 3 calciums to combine with 2 phosphates, 2 of those groupings, to make a neutral compound. So I'm going to write 3 calciums, 2 phosphates, and then remember phosphate, when I look it up, is PO4. That's what phosphate always is. It will never change. That's what phosphate's identity is. So calcium phosphate should be Ca3, parentheses, PO4, and 2 of them. Okay, now I got to do the same thing over here. A lot of people are going to want to go, oh, phosphate's PO4, and there's 2 of them. I'm just going to move that over here. That is not correct. When they recombine, sodium is going to dictate how many phosphates are able to bond with it, or vice versa. So I have to look up these charges as well. Sodium is a +1, and phosphate is a -3. Okay. Now when I look at those, it's a different ratio. I'm going to have 3 sodiums combined with 1 phosphate. But Mr. Throne, there's 2 phosphates over here. Yeah, we're going to take care of that when we balance the amounts. But this is the identity of sodium phosphate. This is the combination that's going to come together and form based on how they're going to achieve stability and equal 0. So I'm going to write 3 sodiums parentheses, PO4, 1. Okay, now remember, I don't write the 1, but it is there. Now you look at this and go, yeah, but hold on a second. This doesn't look like I would expect. If there's two phosphates, don't they have to show up over here? They have to show up, but it doesn't mean they'll have to bond to the same sodium atoms. So now at the very end, we're going to take a look at balancing. Okay, when I go through this progression, I took care of all the charges. Now I've got everything written. There were no covalent compounds in this equation, so I don't have to worry about dealing with prefixes in this stage. Okay, I dealt with all the compounds, and I have a formula for each one that's correct. Now I'm going to balance the amounts. Now I worry about how much of each thing needs to be there. So for example, we talked about how there's two phosphate groupings here. Well, I need two phosphate groupings over here, but if I put a little 2 down there, that gives me a compound that doesn't exist. It's not the correct formula for it. I just need to account for the amounts. So since there's one phosphate here and two phosphates over there, I'm going to put a big 2 out in front. And remember, this 2 gets multiplied through, it's just like math. We distribute it through, and that means there's 2 phosphates because I basically have 2 of these molecules that I'm talking about. Now that 2 times 3, that gives me 6 sodium, so I'm going to put a 6 over here. And I have 3 calciums on the left, so I need to put a 3 right there. Notice we balanced the amounts. Now everything's accounted for, but we didn't do that till the very end after we had the correct formulas. And that's the key. You got to write the correct formulas and then balance the amounts at the very end. That's why I got the green down here at the bottom. We always balance, but it's always at the last. Don't do it at the first, or you get really off track on what the correct formulas ought to be. And that's the general progression we're going to go through. Let's apply it to a couple other situations. All right, I'm going to grab my blue here because I know I'm going to start with diatomics. Okay, boron plus fluorine gives me boron trifluoride. All right, so a new equation. Boron and fluorine are both separate. They're both by themselves. Here they're together, but here they're separate single elements. Fluorine is one of those diatomics. So instead of writing F, I'm going to write F2. Really watch for this. These actually show up a lot more than you would think. Now, boron is not one of those, so I just write B. Okay, so I took care of, there's a diatomic where it showed up. Okay, and I make sure it's F2 anytime I see it that's by itself. Now, once they come together and combine, it doesn't have to be in pairs because now it's combined with boron, and that's going to dictate how many of them there are. So I look at this, I go, all right, charges on ionic compounds. That's not an ionic compound. It doesn't have a metal involved. Okay. How about prefixes for covalent? All right, I see a prefix. That means I don't have to pay attention to charges at all. I just have to write what the name says. I've got 1 boron and 3 fluorines because it says trifluoride. But Mr. Throne, there's only 2 fluorines over here. Yeah, we're going to get to that because we're going to balance the amounts at the end. So now I've got the correct formulas for the single elements. I've got the correct formula for the compound. Now let's balance the amounts. Okay, if we put a 2 in front of this, that gives us 6 fluorines, which is nice. Even numbers work out well. I can put a 3 here, and that gives me 6 fluorines also. And then I can put a 2 in front of this, and I've got 2 borons on each side, and now all the amounts are balanced, but I did that last. Okay, let's apply it to one more that looks more complicated, but it is not. All right, so let's take a look at this last one. We got acetylene, which is C2H2. I wouldn't expect you to know that off the top of your head. I'll give you that formula. Plus oxygen gas gives you carbon dioxide and water vapor. There's more words, but you guys just have to write the meaning of those words. All right, so let's start with diatomics. Are any of these 7 alone by themselves? And I see one right here. Here's oxygen gas all by itself, so we're going to write O2. Okay, but that's the only one I see. This isn't alone, that's a combination. This isn't a single element, that's a combination, and same with this. So that's the only one that's going to be my diatomic. Now I'm going to write the other things here. So I know acetylene is C2H2, put a plus right there, put my arrow, and now I got to look and see what we have to work with. All right, everybody in here knows that water vapor is H2O. I know it says vapor, that just means it's really hot and it's a gas, but it's still just water, H2O. Carbon dioxide, look over here, that's not an ionic compound because there's no metals, but it is a covalent compound. It's got a prefix in di. So carbon dioxide means 1 carbon and 2 oxygens. Okay. So there's my covalent molecule showing up. Now, I just have to balance these amounts. So let's take a look at what we have to work with. This one's gonna take a little bit more effort. I've got 2 carbons on the left. I don't wanna deal with oxygen yet because it shows up in several places. I wanna leave oxygen alone till the very end. There's 2 carbons on the left, so I'm gonna have to put a 2 right here. There's 2 hydrogens on the right. There's already 2 hydrogens on, 2 hydrogens on the left. There's already 2 hydrogens on the right. I don't have to worry about that. That's already balanced. But now I gotta count up oxygens. Okay. 2 times 2 gives me 4 oxygens. And then I've got 1 oxygen over here. When I add those together, I get 5. And this is a problem, because I have 5 total oxygens on this side of the arrow. I need 5 total on this side of the arrow. How am I gonna get 5 when I have to multiply something here by 2? There isn't a number that exists. So our trick to this was, when you get an odd number that doesn't work out, we double everything. And I mean everything. So we're gonna start by doubling the fuel here, the acetylene. Okay? And what that does is it's gonna put this as a 4. And we're gonna put a 2 right here. And when we do that, all the other numbers get twice as big. This becomes an 8. This becomes a 2. This becomes a 10. Everything got twice as big. So now this is a 10. And I need to have 10 total oxygen, so if I put a 5 right here, 5 times 2 is 10, and now it's balanced. 2, 5, 4, 2. Okay. Hopefully you can see in the progression here, the spots that people mess up on are the blue and the red. Almost everybody can balance. It's those other 2 that get people. They try to jump to the balancing part first. So you have to look for charges on any ionic compound, and you have to look for prefixes on any covalent compound. And you have to find any diatomic elements that are by themselves, like fluorine and oxygen. And that's our basics, our basic structure, our basic progression for writing chemical equations.